Life on planet Earth evolved under the influence of a 24-hour light-dark cycle and a 365-day annual cycle of environmental conditions. Biological cells, the basic unit of life, evolved biochemical mechanisms to measure daily and annual time, thus anticipating consequences of a predictably changing future environment. This clock timing mechanism provides for preparatory biochemical shifts that enhance survival in the new environment. In multicellular organisms, such as humans, it is the role of the circadian clock neural system within the brain to synchronize the clock-timed biochemical events among cells of different organs of the body so that the body is temporally organized internally and with the cyclic environment. An obvious example of this daily clock system is the daily sleep-wake cycle. However, beyond the sleep-wake cycle, there are innumerable other daily biochemical rhythms in the body that are temporally coordinated to maintain health with certain biochemical functions operative primarily at certain times of the day. An annual clock system is also functional in the body. This annual clock system in humans evolved from the earliest vertebrate species on Earth over 400 million years ago, under natural conditions to control their seasonal metabolism in a way that ensures that the brain receives enough glucose to stay alive during particular seasons of the year, when little to no food or sugar is available in the wild, since the brain has a near absolute requirement for sugar as an energy source. The brain cannot properly function without an ample sugar supply for even a few minutes. So how can it manage when next to none is available for months? By measuring annual time, the brain clock can anticipate when the low sugar season is approaching and prepares the body to make more of its own sugar and to use less of it in the body so it can be spared for use by the brain. Certain daily rhythms of nerve activity that provide information to the clock change their daily 24-hour pattern of activity with the changing of the seasons of year. Available evidence from studies of various animal species suggests this annual shift in circadian rhythms of neural input activity to and at the brain clock system facilitates the generation of the annual cycle of physiology, including metabolism. One very important nerve signal to the clock is that of a neurotransmitter called dopamine. As we look at the circadian 24-hour rhythm of dopamine activity at the clock in the lean, insulin-sensitive season, which is summer in temperate zones, we see a large number of dopamine molecules released onto the clock neurons in the brain in the morning. This dopamine release is part of the waking mechanism, and in combination with other neural information received by the clock, it initiates clock nerve output signals to the body, telling it what metabolic state to be in. When the circadian peak dopamine signal to the clock is strong at waking, it modulates the clock neuronal messaging system to the body for metabolism to be set towards normal insulin-sensitive metabolism. Insulin action is not antagonized in liver, muscle, and adipose. As such, insulin functions normally to reduce glucose production by liver, facilitate glucose disposal in muscle and liver, and limit fatty acid release from adipose tissue to maintain normal plasma glucose levels. However, in the obese insulin-resistant season, which is winter in temperate zones, when food availability is low to none, and yet the brain still needs a constant supply of glucose to survive, the daily peak activity of dopamine at the clock upon waking is naturally markedly diminished, and this results in different SCN output signals going to the body, again via the nervous and endocrine systems, to increase the glucose supply to the brain. The peripheral fuel metabolism, as a result of this new neuroendocrine signaling from the clock, that facilitates increased sympathetic nervous system activity, increased plasma cortisol, and leptin resistance, now favors the obese, insulin-resistant, less effective state that is able to release more free fatty acids from adipose tissue, make more sugar in the liver, and shunt it to the brain by having the peripheral tissues utilize fat more preferentially over sugar as an energy source. Excess fat is built up by this winter neuroendocrine regulatory system for metabolism in part due to the clock signaling to the body to enhance insulin secretion, which stimulates fat production. Overall, less glucose is able to get into the body and be used by the body, enabling more plasma glucose that is produced by the liver or ingested from meals to be shunted to the brain, while the peripheral tissues increase use of stored fat as fuel. This is an adaptive physiology for survival in adverse environmental conditions of seasonal low food availability. It is also something, however, that we recognize as a pre-diabetes physiology if it is sustained chronically. The human pre-diabetes pathophysiology appears to share this natural etiology, whereby adaptive mechanisms of seasonality have become maladaptive in the setting of the westernized lifestyle, wherein the body becomes stuck in this seasonal insulin-resistant condition all year long. What is the connection between the natural evolved mechanism to become pre-diabetic during seasons of low food and glucose availability and the global rapid onset of this condition in humans? The huge rapid increased incidence of type 2 diabetes cannot be explained by any single genetic defect per se. The evidence argues strongly for environmental factors influencing the genome to induce the disease. A major culprit is the westernized lifestyle. The seasonal clock system that evolved to counter the naturally occurring environmental stress of low no-food availability now appears to interpret the westernized high-fat and sugar diets, disrupted sleep-wake cycles, and daily sociological stress associated with modern societies as impending or immediate stress signals to move the body into its survival mode, the pre-diabetic state, to prepare to supply glucose to the brain. This stress signal to the clock system is in part a reduction in the circadian peak in brain dopamine activity, particularly at the area of the clock to drive the body's metabolism toward insulin resistance that in turn functions to maintain a glucose supply to the brain and survive these westernized stresses. The brain clock appears to perceive the low brain dopamine activity as a key message of ensuing or present life-threatening conditions, similar to ensuing seasonal adverse environmental conditions of low or absent food availability. The changes in metabolism that produce the pre-diabetes state also feed back to the brain to keep brain dopamine low and thus maintain the insulin-resistant state that the body can't easily get itself out of. With the insulin-resistant syndrome typical of type 2 diabetes, one observes many of the same metabolic consequences as of seasonal insulin-resistant syndrome, but these adverse metabolic consequences are now constantly expressed over the entire year, year after year. If the body stays in this state too long, i.e. for more than a season extending to years of time, damage can occur to complex cellular biochemical mechanisms that result in inflammation and reactive oxygen species generation, leading to frank diabetes and its associated pathologies, such as stroke, kidney failure, and cardiovascular disease. One mechanism to treat these underlying neuroendocrine etiological factors that contribute to the genesis of the pre-diabetes type 2 diabetes disease state is to reset the clock output signaling towards the insulin-sensitive organization. This is most effective the earlier in insulin-resistant syndrome progression the intervention occurs, before significant loss of beta cell function and damage of neural circuits in the brain, to maximize beneficial impact of clock resetting of insulin-resistant syndrome. One mechanism to do so is via reinstatement of the normal circadian peak in dopamine activity at the brain clock system, observed in insulin-sensitive states. By doing so, the appropriate dopamine signal is perceived by the clock system that messages the clock to move the body via the neuroendocrine system into the normal, insulin-sensitive metabolic condition at the organ, tissue, and cellular levels. Upon receiving this new neuroendocrine message from the brain clock system, clocks throughout the tissues of the body then shift and begin to synchronize at the organ, tissue, and cellular levels in a manner to maintain this insulin-sensitive condition. By regulating the clocks in the body, together with changes in eating habits and lifestyle, the body is able to move towards a more metabolically controlled, insulin-sensitive state.